In every example problem up till now, the force that's been involved when work is done has been a constant force. So we've defined work as a scalar quantity that's equal to the vector dot product of some constant force multiplied by a change in position or a displacement, which in turn is equal to the magnitude of the force multiplied by the overall displacement times the cosine of the angle between those vectors. Well, here's a case where the force is not constant. We say this is an example of work done by a varying force. So suppose it's given that the force varies with position according to this stated equation. Now, what's this equation really telling us? It says that at time t equals 0, when x also happens to be 0, so we can put an origin right here. X equals 0, at time t equals 0, the initial velocity is 0. So for that given position, that means the initial force being applied by this person is equal to 350 newtons. And as they push it from point A to point B, the force gradually decreases. You could certainly see from this equation that as the position increases in value, then that means the force is going to decrease, right? Because we're subtracting two terms that depend on x. Actually, one depends on x cubed, one depends on x to the first power. Now, I'll leave it up to you to apply your algebra skills to solve this cubic and figure out at what position, how far is this 19 kilogram object pushed until it reaches a moment where the force is equal to 0. Now I'll give you the solution and you can see that it checks out. After it's been pushed a distance of 5 meters, I think you'll see that the applied force is then 0. Let's plug in and verify. So 350 minus 2 times 5 cubed minus 20 times 5. Let's see, 5 cubed is 125, and 2 times 125 is 250. 20 times 5 is 100. So 250 plus 100 gives us 350, and sure, 350 minus 350 would be equal to 0. So that's exactly the case. Initially, this person starts out pushing with an applied force equal to 350 newtons, and by the time it's displaced 5 meters, the force is now 0. So the question would be, how much work was done during that displacement? Well, we couldn't use this equation because we don't know which value of force. We certainly know that the overall displacement is 5 meters. We know that the angle between the two in this case is 0 degrees. But what are we going to put in for the force? Are we going to put in 350 newtons, the force that was being applied at the beginning? Are we going to plug in, well, certainly we won't plug in 0 newtons, then we would get 0 work. So in cases like this, we have to break up the displacement into little incremental bits. So we might view it like this. Instead of considering this overall large displacement that we call delta S, we could imagine each one of these little bits is some small fraction of the overall displacement ds. And ultimately, what we're going to do is break it up into so many little minuscule displacements that ds approaches 0. And so the force over this very small interval can be approximated as a constant force. So what we need to do is say there's a little bit of work done during the first interval. And that little bit of work done is equal to the force within that interval multiplied by that little bit of displacement. And in the end, the total amount of work will be found by summing up all the little bits of work, which means the work is equal to the integral of f ds. Well, keep in mind, this is still a dot product, so I really mean f dot ds. But keep in mind, in our example problem, we're sticking to the case where the force and the displacement are parallel to one another. So it's an example of where the angle is 0 degrees. Right, so we're defining work as the integral of force with displacement, which means in turn it's the integral of the magnitude of the force times the magnitude of the incremental displacements times the cosine of the angle between them. So if we want to find how much work was done In this problem, we just need to substitute this expression for force. So the work done is equal to the integral of 350 minus 2x cubed minus 20x. Well, we're saying ds. S is just a symbol that means displacement. Sometimes things displace entirely on the x-axis, so ds and dx are indistinguishable. Sometimes objects displace exclusively along the y-axis, and so ds and dy would not be distinguished. But if an object displaces along some angle, then we'll just keep it as ds. Or if an object displaces along a curved path, we'll call that arc length ds. So ds is just a more general term for displacement than dx or dy. In this case, we can certainly replace ds with dx. And because this is 0 degrees, cosine theta just goes to 1. Now we need to put in limits of integration, right? What's the initial and final value for x? Well, that's pretty clear. It starts from x equals 0, and as we showed earlier, after a displacement of 5 meters, the force drops to 0. Okay, so this means if the integral can be thought of as the antiderivative, then the amount of work done should be equal to 350x minus 2/4 x to the 4th minus 20 over 2 x squared. We can simplify that a little bit. 350x minus 1/2 x to the 4th minus 10x squared. Of course, this is evaluated from x equals 0 to 5. Now, at x equals 0, our lower limit is very easy. Since there's an x in every term, that's going to just evaluate to 0. So the work done in this case is 350 times 5 minus 1/2 of 5 to the 4th power minus 10 times 5 squared. You might need to grab a calculator for this one. 5 squared we know is 25, and 10 times 25 would be 250, so we got that part. Let's see, 5 to the 4th is 625. Half of that would be 312.5, so we got that part. 350 times 5, that's 1,500 plus 250. That's 1,750. Okay, we got that part. Okay, so 1,750 minus 312.5 minus another 250 gives us a total amount of work equal to 1,187.5 joules. All right, now let me just give you a little more insight into this method for calculating work. How to calculate work. 1, if force is constant, then we'll just say work is equal to the dot product of that constant force multiplied by some overall displacement. In case 2, if force varies, in other words, force is a function of position, then work is equal to the integral of f dot ds, which is the integral of f ds cosine theta. We're going to find in a future lesson there's a third way to do it that has to do with calculating the area of a particular graph. I'll let you ponder that. But for more insight about this form of the equation, we showed in the previous lesson the work kinetic energy theorem. And we said that work is equal to a change in kinetic energy. So let's think about this. If work is equal to the integral of F dot ds, let's consider the case where we're dealing with a net amount of force. Remember, we always choose the x-axis to be the axis of displacement. So when dealing with net force, it's always parallel to our displacement. So we're going to call this the net amount of work should be found by taking the dot product of the net force with displacement, which is just net force times the magnitude of displacement. All right, that means net work is equal to the integral of ma ds, which is mass, times the integral of dv dt times ds. And we could rearrange that and say that's the integral of dv times ds dt. But what is ds dt? That's just velocity. So net work is equal to mass times the integral of v dv. And the integral of v dv, well, let's just integrate it from some initial velocity to some final velocity. This means net work is equal to m times 1/2 v squared, evaluated from v initial to v final. So net work is equal to 1/2 mv squared minus 1/2 mv initial squared, which is the same result we got in the previous lesson when deriving the work kinetic energy theorem based on constant force. As long as we define kinetic energy as a quantity we calculate as 1/2 times an object's mass times its speed squared. So there we have it. The net amount of work done on any object is always equal to its change in kinetic energy. This is true whether force is constant or force varies. That's nice to know. Thanks for watching.